Hello, my name is Andrew Cabral, and today I'll be presenting my CS392S final compiler project. The goal of this project was to build a complete compiler pipeline for a functional language called Lambda, starting from theoretical foundations in Lambda calculus and ending with executable JavaScript output. The presentation follows the natural order of the pipeline. We will start with the pure Lambda calculus theory the language is grounded in, then cover the Lambda language itself and its type system, followed by the three implementation components, the type checker, the compiler, and the JavaScript emitter. We will finish with the four test cases that validate the whole system. Moving on to the foundations of pure Lambda calculus. It was introduced by Alonzo Church as a minimal formal system for expressing computation using only function definitions and applications, the foundation of which lies in three syntactic terms, which are one, variables, which are any name, for example, x, y, or z; two, abstractions, which are the formal definitions for anonymous functions. In the example in the slide, if m is a lambda term and x is a variable, then lambda xm is a lambda term. This represents the anonymous function with parameter x and body m. And three, applications, where in this example, an application mn represents calling the function m with argument n. Despite having just three syntactic terms, it's Turing complete. In this project, those three forms are the foundation that the interpreter, type checker, and compiler all operate on. Moving on to alpha equivalence and substitution, which are two foundational concepts that govern how lambda calculus computes. Alpha renaming is the operation of consistently renaming a bound variable throughout its scope. For example, in lambda XX, we can rename x to y everywhere it is bound, giving lambda yy. This is valid as long as the new name does not clash with any existing free variable in the body. Substitution is how function application is formalized, replacing every free occurrence of x in M with n. The danger of substitution is variable capture, where a free variable in N accidentally gets bound by a binder already present in M, changing the meaning of the term. To avoid variable capture, capture avoiding substitution is utilized, which entails renaming the bound variable using alpha equivalence first, which means choosing a fresh name that cannot collide at any stage of computation. Moving on to beta redex and evaluation strategies. A beta redex is an abstraction applied directly to an argument and a computation step waiting to happen. Performing that step is a beta reduction, which substitutes the argument into the body to produce the contractum, which is the resulting expression after you perform a beta reduction. The concrete example seen in the slide shows lambda x plus 1 applied to 5, which reduces to 5 plus 1. In this case, the contractum being 5 plus 1. The two main evaluation strategies differ when the argument gets evaluated. Call by value evaluates the argument to a value first. Call by name substitutes the unevaluated argument directly and only computes if it is actually used. Lambda's stream construct uses call by name style funcs to represent infinite sequences inside an otherwise eager language. Moving past evaluation strategies and onto Lambda itself. Lambda is a dynamically typed language whose programs are Python data class trees. The basic constructs cover integers, booleans, and string literals, and variable lookup via dvar. Functions are expressed through dlam for single argument lambdas with inferred parameter types, dapp for function application, and dfix for recursive functions, which bind the function's own name within its body to enable self-reference without built-in loop constructs. There are also three operators: unary dop1, binary dop2, and the flexible dopper, for cases like the three-argument array set that don't fit into one or two expression forms. Control flow is handled by DFO, the language's sole conditional form, which evaluates a Boolean test and branches accordingly, and dlet, which binds the result of an expression to a name and evaluates the scope with that binding in effect, which is the only way to introduce a named value outside of a function parameter. Tuples are constructed with dtup and deconstructed with dfst and dsnd, each backed by a runtime assertion that the argument really is a tuple rather than a graceful type check. Lists are immutable and singly linked, built from a dlist nil base case and a dlist cons nodes that prepend ahead onto an existing tail. Moving past that to streams, arrays, and typed forms, streams introduce laziness into an otherwise call-by-value language. D-lazy wraps an expression as a thunk, meaning a suspended computation not evaluated until explicitly forced. D-STCN cons pairs an eager head with a lazy tail, and together with DSTCN nil as the base case, this lets infinite streams be represented and consumed finitely. Moving on to arrays, arrays come in two forms: one initialized by constant value and one by function over indices. Finally, the explicitly typed forms dlam1, dfix1, and dano lets you state types outright rather than relying on inference, with dano in particular verifying its annotation via unification rather than trusting it blindly. Now, I would like to move on to the simple type system. The STYP type has three building blocks. Base types like sint, bool, and strn represent concrete, already known types. Unification variables called stxyz start out unresolved and get pinned down as constraints accumulate during type checking. And compound types cover functions, tuples, lists, arrays, plus the stream pair st strm and ststcn for suspended versus forced stream nodes. Inference itself works by allocating fresh unification variables at binders like dlam and dfix, then resolving them based on how the parameters are actually used. When inference alone isn't enough, the explicitly typed forms dlam1, dfix1, and diano give you what is essentially an escape hatch, and diano specifically check its annotation through unification rather than just accepting it on faith. Now moving on to the type checker, DEXP-OFT-POO is the first point of the type checker, which sits between the interpreter and the compiler. Its whole job is to begin type checking with an empty context, calling DEXP-OFT-PCTX with SCTX nil, since at the top level there are no variables in scope yet. It returns either the inferred STYP of the expression or none if the expression doesn't type check at all. DEXP-OFT-PCTX is where the actual recursive work happens. It walks through the DEXP tree and accumulates bindings into the context as it goes, and infers a type for every subexpression along the way. Every recursive call into DEXP-OFT-PCTX is checked for none immediately, so a failure anywhere in the subexpression propagates straight to the top rather than getting ignored or causing a crash partway through. This also means that DEXP-OFT-POO itself never raises an exception on bad input. The none return is the only given signal, which is what makes it safe to call on arbitrary, possibly malformed programs. Some operators need their argument to have a specific shape, not just any concrete type. ListHead, for instance, only makes sense if the argument is actually a list. The SDYZ helpers handle this. If the argument's type is already the right shape, they confirm it. If it is still an open unification variable, they pin it to that shape on the spot, which is what lets something like a recursive list function get type checked without ever writing out an explicit list type by hand. Every single one of these checks and every recursive call into DEXP OFT PCTX is immediately tested for none before the type checker does anything else with the result. There's no assertion anywhere. The type mismatch or an unbound variable just returns none, and that none rides all the way back up to DEXP OFT POO without crashing anything along the way. DELEM1, DEFIX1, and DEANO exist for the cases where you don't want to leave it to inference. Instead of allocating a fresh unification variable, DELEM1 and DEFIX1 take the parameter and result type directly as written and check the body against them. DEANO does the same for arbitrary expressions. It still runs inference on the expression, but then unifies the result against whatever type that was written down, allowing the type checker to verify the annotation. Now I would like to touch on the compiler. The start of the compiler is DEXP comp 000, which calls DEXP comp env with an empty compile time environment and returns a DCMP, a record pairing a flat instruction list with a result register. The compile time environment maps variable names to registers and is extended at function and let binding boundaries. Three groups of globally unique registers are allowed by incrementing class level counters. TTMP new for temporaries, TARG new for function parameters, and tfun new for function names. Every case in DEXP comp env follows the same uniform pattern. Compile each sub-expression, concatenate the instruction list in evaluation order, allocate one temporary for the expression's result, append a single instruction that computes it, and return. Functions are the one not flat case. DE-lam allocates fresh function and argument registers, extends the environment with a parameter binding, compiles the body in that extended environment, and wraps the result in a single ins_fun instruction whose body field is itself a nested DCMP, making the instruction stream tree-structured at function boundaries. DE_fix compiles identically but extends the environment twice, once for the function's own name to enable self-reference and once for the argument. DE_let is a zero-cost abstraction. No instruction is emitted. The binding lives purely in the compile time environment, and type annotations are fully erased. DE_lam1 and DE_fix1 compile exactly as their unannotated counterparts. DE_lazy compiles like DE_lam, but with no parameter, wrapping its body in INS lazy as a deferred zero-argument computation. This ties into the JavaScript emitter because it takes a DCMP and produces a complete, self-contained JavaScript file that can be written to disk and executed directly with Node. The output begins with JS Prelude, a fixed block of helper functions that gives lambda's structured values concrete JavaScript representation. Lists and stream nodes are the same object shape, nil true for empty, nil false for head and tail with concells, with the difference that a list tail holds the next node directly, while a stream's tail holds a zero-argument thunk. Arrays map to native JavaScript arrays with slice-based functional updates, and tuples become FST/SMD objects. Each instruction then emits a let statement using the register name directly as the JavaScript variable name. Within the emitter, there are two instruction cases that need special handling. Ins_fun emits a named function declaration using the function's own register name. This is what allows recursive functions compiled from DEFix to call themselves by name in the output. Ins_lazy emits a zero-argument arrow function, which defers execution until the closure is expressly called, directly mirroring valfunc at runtime and preserving lambda's lazy semantics in JavaScript. Instructions with nested bodies, for instance ins_fun, ins_if, and ins_lazy, recurse the emitter at a deeper indentation level, with a return or assignment statement surfacing the nested result to the outer scope. Operator translation is handled by the op1.js and op2.js dictionaries mapping operator names to JavaScript expression strings, with integer division using math_trunc to match lambda's truncating semantics. Now to conclude, I would like to cover my test cases. The test suite has three parts, each pushing all four pipeline components through the same expressions. The all constructs sweep checks every DEXP constructor and includes a deliberate ill-typed expression to confirm the type checker returns none cleanly rather than crashing. The 8 Queens puzzle stress tests deep recursion by counting all 92 solutions, verified through the interpreter, compiler, and executed JavaScript. The sieve of Erastesis builds an infinite lazy stream of primes using DE_lazy and DESTCN cons, confirming the thunk pattern survives compilation all the way through runnable JavaScript. Finally, the church-encoded factorial computes factorial 5 equals 120 using only pure lambda calculus functions with no built-in tuples, proving higher order functions compile and execute correctly through every step of the pipeline.